Hello everyone. In the last video we have seen constructional details of stator, and in this video we will try to understand how AC winding is placed in stator slots. Right? We will discuss about AC winding. AC winding. AC winding. In stator slots we will keep winding, and that winding is prepared by using coils, right? So if you observe coil may be like this. It consists a number of turns. Let me take, it is having a number of turns, and this number of turns can be decided based on slot width and slot depth, right? So let me take this as one coil 1, right? So we can use these coils to form winding, right? Actually, while designing winding for any machine, this number of turns depends upon voltage rating. If you want to design machine for a higher voltage purpose or higher voltage rating purpose, in such case we can use more number of these type of coils, right? We can connect those coils in series. Let me take one more coil here in similar fashion like this, which is having same number of turns. Let me call this as a coil 2. Now in order to increase voltage rating of that machine, these two coils can be connected in series like this, so that voltage capacity can be increased, right? Voltage rating can be increased, right? So this is the connection for voltage requirement, to meet voltage requirement, right? Sometimes we need to design machine winding with higher current rating or higher current capacity. In such cases, what we can do, we can use similar coils, but they are connected in parallel, right? For example, see, this is coil 1, which is having a number of turns, and let me take another coil, which is coil 2. It is also having same number of turns. So in order to increase current capacity of the machine winding, what we are doing here is we can connect these two in parallel. Like this we can connect, right? So coil or winding representation point of view, we can use this symbol, right? When it go for actual representation, coil can be like this. I mean, coil can be prepared like this, right? See here, coil consists a number of turns. For example, let me design one coil with 1 turn, right? First we will try to understand coil with 1 turn. Coil with 1 turn. 1 turn. So if you want to design 1 turn coil, how it is prepared, right? I can say that turn consists of 2 conductors. Let me draw here. This is the one conductor, and this is another conductor, right? This is conductor 1 and this is conductor 2, and I can join these two conductors by using end connections like this. This is back end or end connections, right? And this is front end connections like this. And now we can say this is 1 turn. 1 turn consist 2 conductors. This is first conductor, and here it is second conductor. Now we can call it as turn as well as coil. Why? Because first we are designing coil with 1 turn. So if you want to design coil with only 1 turn, it consists only 2 conductors, right? Therefore, this turn we can call it as coil, right? So if I am calling this as a coil, if I am calling this as a coil, this region or this set of conductors, here actually it is having only one conductor, and sometimes if coil is having more number of turns, we will be getting more number of conductors here. So this set of conductors we can call it as a coil side. Coil side. This is one coil side. This is another coil side. This is another coil side. So therefore I can say each coil consists two coil sides. Each coil side or each coil consist two coil sides. Two coil sides. Two coil sides. Right? Each coil consists two coil sides. Right? And now if you observe each coil side, how many conductors are there? Actually here we are having 1 ton. 1 ton means 2 conductors. So total conductors in this coil is 2. Total conductors in this coil is 2. So I can write here total conductors in a coil is 2, right? So as we are taking only 1 ton, so that it is having 2 conductors, right? If I take n tons, then what happens? N tons into 2. So n into 2 conductors. N into 2 conductors, right? So total conductors in a coil is 2n, right? Similarly, if I take total conductors in coil side, right? This we called it as a coil side, na? So total conductors in coil side is equals to, as per this diagram, I can say only one conductor. So that is applicable for 1 ton. But when it comes to n tons, it is going to have n conductors. Total conductors in coil side is n. Total conductors in coil side is n, right? So here remember this n is number of tons, where n is number of tons, n is number of tons, right? So here we have seen 1 ton coil, right? So if you go for higher tons, let us see how it will be, right? So here we will try to draw at least 3 ton coil, right? Let me draw here 3 ton coil. 3 tons coil. 3 tons coil, right? 3 tons coil, how it is represented? How can we draw it? It will be like this: 1, 2, 3, and here it is 1, 2, 3, right? And let me take this first conductor, or let me join first. This is how it is connected. See, this is how it is connected. Right? Now I can say this is 3 ton coil. Right? This is the ton 1, ton 2, this is the third ton. Right? And in this case, I can say this set of conductors we can call it as coil sides, and this is also another coil side, coil side, right? This is first coil side and this is the second coil side. And if you observe total conductors in this 3-turn coil, previously what we have written, total conductors in coil, conductors in a coil is equals to, previously we have written it as 2n. So how many turns are there? 3 turns are there. So here n is equals to 3. So 2 into 3, which is equals to 6, right? See here, first, second, third, fourth, fifth, sixth conductor. Total 6 conductors are there. And if you see total conductors per coil side, total conductors per coil side, total conductors per coil side is equals to, how much we have written? It is equals to n. And how much here, n value? It is 3. So therefore we can put it as 3. See, again it is matched. 3 turns per this coil side, 3 conductors per this coil side, and remaining 3 conductors are there for this coil side, right? And this is how we can prepare coils in order to design stator winding, right? In stator winding, in generally, polyphase machine, we can use a 3-phase winding, right? That 3-phase winding can be connected either in star fashion or delta fashion. But first of all, we need to understand how this winding is placed physically, right? In that stator slot, how this winding is placed physically, that we need to understand. So for that purpose, we will go to stator construction part, right? Stator designing part. And here, try to remember this coil we have designed. So like this, we can design n-turn coil, right? This is the 3-turn coil. Like this, we can design n-turn coil, and such n-turn coils we can use. We can connect in series or in parallel fashion. In order to meet voltage requirement or voltage demand, we can connect a few coils in series, and in order to meet current requirement or current carrying capacity, we can connect some of the coils in parallel, right? For example, if you see, if I take each coil is having capacity of let me take 1000 volt. For example, if we are having coil like this, which is having say some n number of tons, and it is having capacity of 1000 volts, right? And having current capacity of, let me take 100 ampere, right? This is the coil rating. And now my machine need to design with 3 kV, right? This is the one coil capacity, but I want to design each phase capacity as 3 kV voltage capacity, and current capacity is, let me take 200 ampere. In such case, how these coils are used is, let me take here this as coil 1, and I can take, in order to meet this voltage requirement or voltage demand, how much it has given, we need to design this run. Actually, design 3 kV voltage capacity, that is 3000 volts voltage capacity, and current capacity of a particular phase winding is 200, right? So for that purpose, first of all, I am checking voltage requirement. So voltage requirement, we need to meet 3000, but our each coil is having 1000 volt capacity. So in order to increase total winding capacity to this 3000, what I am doing here, I can take 3 coils here, right? Coil 1, this is coil 2, and here it is coil 3. Let me take this as coil 3. Now what I can do, all these 3 coils I can connect in series. So that what happened, this is the 1000 and here it is 1000 and here also it is 1000. So if you add, this total is going to be 3000. So now we met with voltage requirement, but still current capacity is not reached to the requirement. So here I can say each coil is having capacity to carry 100 ampere, but my winding, this three-phase machine winding or this particular phase has to carry 200 ampere. So for that purpose, what I can do, I can use another set of coils like this. Let me take coil 4 and here it is coil 5 and here it is coil 6. Coil 6. Right? Again this 4th coil, 5th coil, 6th coil, again it is connected in series. And now I can say it is having capacity of 3000 volts. But this string or this particular branch is connected in parallel to existing one. Like this. Like this. We are going to connect it in this fashion. Right? So now I can say this path can carry 100 ampere and now this path can carry another 100 ampere. So therefore I can say total current carrying capacity of this particular phase, if I treat this as a phase, R phase or Y phase or B phase, sometimes it may be represented with other lettering also, A, B, C, U, V, W, X, Y, Z, whatever it may be. Right? So if I consider this as a phase, see voltage requirement is met by using this connection. I mean by connecting coils in series, we met voltage demand. Right? And coming to the current capacity requirement, to meet this current demand, what we did here is, again we have taken same set of branch, but that is connected in parallel. So whenever it is connected in parallel, both the setups, I mean this series combination and this series combination is going to have same voltage capacity, that is 3000 volts capacity, which is 3 kV. But coming to the current capacity, each branch or each path is having a capacity of 100 ampere. Right? We require 200 amperes to design to carry each phase. So for that purpose, I am adding extra branch. I mean, I am adding in parallel to existing one, same setup. So that this also carry 100 ampere. So now I can say this overall phase can carry 200 ampere of current. So this is how windings are designed. This I can say it is a phase winding. Right? Let me take it as a phase winding. Phase winding, right? Like this, we can prepare 3 phases. If you want to design 3-phase winding, we require 3 setups, such type of arrangements. So we can design 3 such type of arrangements, right? So this is how we can connect these coils, right? So understanding purpose, we can represent coils with this inductor symbol, but when it comes to practical, it will be like this, right? Each coil is going to have coil sides, right? 2 coil sides, and these coil sides we are going to insert in that slots, stator slots, right? And after inserting that, we can connect as per our requirement. In order to meet voltage demand, we will connect a few coils in series, and also in order to meet the current demand, we can connect coils in that series combinational coils in parallel to existing one. Right? So this is how it will be designed, right? Phase winding or any individual phase winding can be designed, right? So let us move to constructional point of view. I mean stator slots diagram, and there we will see how these coil sides are placed. There we will see how these coil sides are placed. Right. Now let us try to design our stator structure, right? Actually, constructional point of view, we have discussed this stator details very clearly. I mean, it consists of stator frame, stator core, and how what kind of structure it is having, and how stator core is prepared, and how slots are prepared on stator core inner periphery. All those things we have discussed. So in this diagram, what I am doing here, I am not showing stator frame, stator core separately. Just I want to draw only one setup which represents a stator, and it consists of slots, right? I want to show a stator diagram, and on the stator I want to put some slots, right? So let me draw that. So this is stator, this is stator, and it consists huge number of slots like this, slots, huge number of slots over here like this. These slots are there on inner periphery of stator core, right? Here I am not showing that stator frame and stator core separately. Remember, these slots are there inner periphery on stator core, right? Actually, like this, there are plenty of slots are there, right? Many number of slots are there, and in these slots we are going to accommodate coil sides, right? Previously we have seen coil sides, na, right? So that coil side we are going to accommodate, right? So here let me take coil with 1 ton, right? Let me take coil with 1 ton, coil with 1 ton, right? For understanding purpose, I am taking coil with 1 ton, but practically coil consists n number of tons, right? And more number of coils are connected in series to meet voltage requirement, and set of coils are connected in parallel to existing one to meet current requirement, right? So here I am going with coil with 1 ton, 1 ton, 1 ton. So 1 ton means each coil side consists only one conductor like this, and this is back end connection, and here it is front end connections. Let me give numbering or naming to these conductors. This is my first conductor, or R conductor. Let me take, this is R phase, R conductor, and this is R dash conductor, and here this is R end, R dash end, right? Now what we are going to do, we need to insert these R phase winding in this stator slots, right? We need to insert this R phase winding in this stator slot, right? So for that purpose, what we can do, as I have taken only one coil, right? I have taken only one coil, that too it is having only 1 ton, right? It is having only one coil and only 1 ton. So whenever it is having only one coil and 1 ton, now I can say coil side consists only one conductor. So that one conductor we need to put inside this slot, right? Actually, see, this diagram is two-dimensional view diagram, right? So if I draw three-dimensional view, how it will be? It looks like this, right? Right? It consists of stator slots in this way, right? Here also there are stator slots like this. So it will be there. But I am not interested in this three-dimensional view diagram. Why? Because this two-dimensional view is sufficient to represent that, to understand the concept. So for that purpose, what I am doing here is, I am going with this two-dimensional view diagram, and in this two-dimensional view diagram, I need to insert this phase winding. Let me take, this is R phase. Let me put first one phase, then I'll try to analyze what happens when you give excitation to this phase, right? So after that, we will try to put other phases also, right? We need to design 3-phase winding, na? So we need to put 3 phases here. So before going to put all the 3 phases, first we will put one phase, and we will try to understand what happens exactly inside this machine. After putting phase winding, if you give supply, what happens exactly, that we need to understand. So if you see here, see, this is the coil, and it is having 2 coil sides, and as per our assumption or our understanding purpose, we have taken coil with 1 ton. So whenever we have taken coil with 1 ton, coil side consists of only one conductor. So if you see this as a conductor from 3-dimensional point of view, it looks like this, right? This is the R conductor, right? So this R conductor, if you see from front side, it looks like a circle. It looks like a circle. So these shape I am going to represent here in these slots. So which tells that it is a conductor. So therefore I can say here, this is a conductor. Now I have kept here, right? And another conductor, that is this one, second coil side conductor, I am going to keep here, right? That is second conductor. Now let me take current direction in this way. Here current is going through the R conductor in this direction, and current direction in R dash conductor will be like this. And if you observe, this is going away from us, right? This is going away from us. So whenever it is going away from us, I can represent that current with cross mark, and current which is coming towards us, right? Towards us means I am taking in this direction. Current is coming towards us means I am taking in this direction. So this current direction I can take it as dot notation like this. So if I represent here, this upper one as cross and lower one as dot, right? Upper one as cross and lower one as dot. Right, 1 minute, I will draw this diagram one more time. Right, see here, I have drawn this diagram in this way. Again, similar diagram I have drawn, but instead of showing 3-dimensional view and many number of slots, I am showing only 2 slots in order to understand the concept, right? And in these slots, we need to place these 2 coil sides, right? Here coil side is having only one conductor, so that I need to show one conductor here. So here I can show this is my first conductor which is having cross mark, that is R conductor, and other end conductor that is dot mark, which can be represented with R dash, right? Now, if you give excitation to this single phase coil, right? This is single phase coil. It may be R phase, but it is single phase. So if you give excitation to this one, that means AC supply. If you give AC supply to this, if you give AC supply to this coil, what happened? What is the pattern of that single phase supply? It is a sinusoidal wave, right? It is a sinusoidal wave. So whenever it is sinusoidal wave, as per this pattern, current will flow, right? So if you observe this current pattern here, during positive half cycle, see at origin current is 0. So that current is 0 means we should not represent any current here, right? And after that, what is happening? After omega t equals 0, current is increasing. As current increases, what will happen? Flux production increases. See, flux production increases. So how flux is produced here? We need to apply right hand grip rule, right hand thumb rule. We have to apply here, right? So if you apply right hand thumb rule, this is the right hand thumb rule, right? This is the right hand thumb, and we need to project a thumb in the direction of current. So cross mark current represents that current is going away from us. So away from us means current is entering into the plane. So that's why try to represent thumb in current direction, which is entering into the plane, and remaining forefinger curl represent flux around the conductor, right? So as per that, I can say cross conductor can produce flux around it in clockwise direction. And coming to lower side, see it is dot notation. Dot notation means current is coming towards us. So if you represent that current with the thumb direction, which is pointing towards us, and remaining forefinger curl represent flux around the conductor, which is there in anti-clockwise direction. So therefore, I can show here flux direction here is anti-clockwise like this, right? Now, this is how flux around the conductor is produced, right? So as current magnitude increases from 0 to towards some value or towards maximum value, what happens? Amount of flux lines around the conductor increases, right? For a simplicity or for simple understanding purpose, I have drawn only one loop around the conductor, but practical machine or practical conductor produces many flux lines around the conductor, and the quantity of the flux line around the conductor depends upon magnitude of the current. If magnitude increases to higher and higher, flux produced around the conductor is also increases to higher and higher. If it is decreasing, for example, if you take sinusoidal wave from 0 degrees to 90 degrees, what happens? Current magnitude increases, right? Increases till maximum value, right? So in that period, what happens? Flux around the conductor will be increases. But after 90, that is 90 to 180 degrees, what is happening here in sinusoidal wave pattern? It is decreasing. See, it is decreasing. Maximum value to, again it is decreasing to 0. So by the time what will happen? Around the conductor, flux quantity decreases from maximum value to towards the 0. Like this, what will happen? During positive half cycle, flux around the conductor will be produced in this direction. Therefore, I can say, see, if you observe this upper conductor flux path in this region, see it is there in the direction, in this direction. And here also, if you see this this flux path, it is also there in this direction. So therefore, I can say during positive half cycle, flux can be produced along with this axis, right? So after completing positive half cycle, what happens here? Right. See, after completing positive half cycle, what happens here? Negative half cycle starts. If negative half cycle starts, what happens? Current direction is going to reverse now. So this current direction we have given cross and dot for positive half cycle. Right. Please consider this direction, upper conductor or conductor as cross mark for positive half cycle, and R dash conductor is having dot mark for positive half cycle, right? So after completing this positive half cycle, what happens? Immediately negative half cycle starts. So whenever negative half cycle starts, I can say current is flowing in opposite direction, right? Previously it is positive, now it is negative half cycle. Previously a positive half cycle, now it is negative half cycle. So therefore I can say it is the opposite current. If it is opposite current, then what happens? Now R conductor can be shown with dot notation and R dash conductor can be shown with cross notation. This is for negative half cycle. Negative half cycle. Negative half cycle. And previously how we have taken for positive half cycle? For positive half cycle we have taken cross mark for R conductor. Cross mark for R conductor and R dash conductor shown with dot mark like this. This notation we have followed. So if you see here during negative half cycle, what will happen? This cross will become dot and lower dot will become cross. That means here flux around the conductor is going to be anti-clockwise because of dot, and here it is going to be clockwise. So under that condition, again what happens? See here, let me put here with another color. If I take this as a dot and this as cross, this as a, see, upper conductor as dot and lower conductor as a cross for negative half cycle. So dot conductor can produce flux around the conductor in anti-clockwise direction like this, and cross conductor can produce flux around the conductor in clockwise direction. Now see this. See how flux is produced now during negative half cycle. It is produced in reverse direction. Previously, during positive half cycle, see the direction of the flux. It is flowing from right side to left side. Now if you see this green color direction, it is flowing from left side to right side at both the conductors. If you take upper conductor and lower conductor, same thing is happening. Therefore now I can say during negative half cycle, axis of the phase flux or axis of this R phase flux is going to be along with the same axis only. The thing is that during positive half cycle, it is projected towards left side. Right? It is projected towards left side, from center to towards left side. Right? This is the direction how it is projected. Right? This is for positive half cycle. Positive half cycle. But after positive half cycle, immediately negative half cycle is coming into picture. So because of that negative half cycle, what is happening? Flux is projected in this direction, right? Along with this axis, right? So this is for negative half cycle, right? Now what happens? Depending upon this flux direction, we can decide how poles are created, right? So this direction can decide how poles are created. For example, if you take positive half cycle, in positive half cycle, what is happening here? Flux is flowing in this direction. See, right? For positive half cycle, upper one is cross, lower one is dot. So flux is flowing in this direction. If it is flowing in this direction, therefore I can say flux lines having direction from this direction, in this way, right? And it enters in this way. It enters in this way, right? Now, by using this direction of the flux, we can decide what kind of poles can be produced here, right? If you take general bar magnet, how we can represent, for example, if you take this as bar magnet, which is having north and south, and how flux lines are projected, always flux lines flows from north region to south region, right, through the air gap. So this is how the path of the flux. By seeing this diagram, can I say wherever the flux lines are leaving from the core or bar magnet, that region here we represented as north, right? I'm taking in this way. Wherever the flux lines are leaving from the region or magnetic magnet, that region we have represented here north pole, and wherever the flux lines, I mean in whichever the region flux lines are entering, that region we represented with the south. So by using the same concept, if I want to represent here poles on this stator, see from this region flux lines are releasing, right? Flux lines are leaving from this region. So therefore for positive half cycle, this is going to be north pole, and here flux lines are entering. See, these flux lines are entering in this region. Therefore I can say this is south pole. And this is how poles are created. right? And this is how poles are created. And this is applicable for positive half cycle. And if you go for negative half cycle, in negative half cycle, what happened? Current direction reverse. If current direction is reverse, then what will happen? This conductor will be taken as dot conductor, and this conductor will be taken as cross conductor. So if it is upper one is dot and lower one is cross, then flux direction will be from left side to right side. If flux direction is from left side to right side, what will happen? From this region, flux will release, and here it will enter, right? For negative half cycle, from this region, flux releases and it will enter. So as per our discussion, wherever the region flux lines are releasing, that will be taken as north pole, and here it will be taken as south pole. This is for negative half cycle. Remember, negative half cycle, negative half cycle, negative half cycle, right? And here this is for positive half cycle. This is for positive half cycle, positive half cycle, positive half cycle, right? This is how poles are created, right? Poles are created, right? When you give excitation to that winding after placing the phase winding, right? Like this, we have to place all the phases, right? Actually, we are discussing about three-phase induction machines, right? In that three-phase induction machine, we need to provide three-phase winding. So before providing that three-phase winding, first we need to understand if we provide single-phase winding on the stator, and if we give excitation to that single-phase winding, what exactly happens? We need to understand, and that is what we have seen till now, right? And from this diagram, we need to understand important points, right? So what are that important points here is, see how many coils we used here. I have used only one coil now, right? I have used only one coil, right? And that one coil I have inserted, right? That one coil is having two coil sides. So one coil side I have kept in upper slot, and other coil side I have kept in lower slot, right? And if you give excitation to this one, how many poles are created here? Can I say two poles are created during positive half cycle? Here north and here south. So I can say during positive half cycle, two poles are created. And if you take negative half cycle also, during negative half cycle, what will happen? This green color poles are created. This side south and this side north. And during negative half cycle also, again it is two poles. So from this one, I can conclude that in order to establish two poles, we require one coil, right? In order to establish two poles, we require one coil, right? Two poles, one coil, right? Can I write here? In order to establish poles and coil, right? So here how many poles are created? Two poles are created. And how many number of coils we use? Only one coil. So therefore, can I say here, in order to create P poles, we require P by 2 coils, right? Depending upon pole requirement, we can decide how many coils it requires, right? As I said previously, number of coils we are using to meet voltage requirement, right? Not only voltage requirement, we need to see from poles point of view also, right? That is also important, right? So in such case, I can make this as a generalized one, right? In order to design machine with P poles, we need to use P by 2 coils, right? Let us go to two coils also, right? So here we have taken only one coil. Instead of taking one coil, let us see by taking two coils, right? By taking two coils, we will try to put those conductors here, and then we will try to analyze whether it is going to give same analysis or not, right? In order to produce P poles, whether it requires P by 2 coils or some other value, that we will try to see, right? This is the one important point we need to understand. And other important point is, see, during positive half cycle and negative half cycle, this flux magnitude is increasing along with this axis only, increasing or decreasing with along with this axis only, right? If you observe that, see, whenever current is at origin, that is at 0, current is 0, flux is 0. If flux is 0, then I cannot represent any flux path actually, right? So after that, what will happen when you move from omega t equals to 0 degrees to say some 45 degrees, what will happen? Current is going to gain some magnitude, right? It is going to increase some magnitude. So whenever it increases some magnitude, what will happen? Flux produced by these conductors also increases. Therefore, under that condition, I can say it is having some length, right? As it is producing flux na, so that flux is going to have some magnitude na, or some quantity na, so that can be represented with phasor, right, on this axis, right? It is there along with this axis only. So in such case I can represent arrow with this much length, right? After 45, that is at 90 degree we are having maximum current na. So whenever current is maximum, flux production by the conductors or coil is also going to be maximum. So I can represent with larger length, right? After 90, if you take another 45 degrees, right, that is at 135. At 135, what is happening? Again current is decreasing. As current decreases, what will happen? This arrow length decreases to here again, right? Again 135 to 180, again it is decreases to 0. So if you see the positive half cycle, see from 0 to 45 degrees, 90 degrees, then 90 degrees to 135 degrees, 135 to again 180. So along with the same axis, flux magnitude is varying. So therefore we represented that variation with a phasor, right? If you observe this phasor length, it is increasing from 0 to 45, 45 to 90. Next 90 to 135, 135 to 180. Right, this is what happens, and exactly happens with negative half cycles also. If you see here with a negative half cycle, see this is at 180, right? This dot at 180. So 180 plus 45, 225. 225, it may be here. Then plus 45, that is 270. It may be maximum. 270 means it is negative maximum. So therefore, in other direction, it will be maximum value, 270. After 270, 315. 315 means again it is decreasing. See, maximum to it is some finite value, it is decreasing. So again this phasor decreases. Again 315 to 360, again it reaches to 0. So therefore finally I can conclude that when you give excitation to single phase, what will happen? That single phase winding can produce stationary flux. So why I am telling here stationary flux? It is not rotating. These phasors are not rotating. Na? Therefore we cannot say it is rotating magnetic field. We can say it is a stationary magnetic field, but magnitude point of view, it is pulsating, right? This is the second important point we need to understand, right? This is the second important point we need to understand. So let me write that 2 points here. To design p-poles, first point is to design p-pole machine, p-pole machine. To design p-pole machine, we need P by 2 coils. P by 2 coils as per establishment of these poles, right? So here, as per this analysis, I have written to design P poles, we require P by 2 coils. This is first important point. And second important point is single phase winding. It may be R phase or Y phase or B phase. It can be anything, right? Single phase winding can produce stationary magnetic field. This is very important. Stationary magnetic field. But its magnitude is pulsating. Its magnitude is pulsating. These 2 points are very, very important, right? From this discussion, right? So we will try to analyze same phenomena with 2 coil, right? This happens with 1 coil. Na? This discussion we had with only 1 coil. So let us try to discuss with 2 coils. Right. See here, I have taken 2 coils, right? This is coil 1. And this is coil 2. Again, I have taken only 1 turn per coil here, right? This is coil 1 and coil 2, which are connected in series, right? In order to meet voltage requirement. So these coils, how I am going to arrange? If you observe this diagram, as it is having 2 coils now, so total coil sets are how much? 4 coil sets, right? First coil is having 2 coil sets. Second coil is also having 2 coil sets. Right, so these 4 coil sets we need to put here in stator slots. So for that purpose, I have kept here 4 slots, right? And if you observe this, I'm going to put, see here, R1 coil set and See, I'm keeping R1 coil side in this one, and as previously we have taken this current as cross mark now. So cross mark, and let me put R1 dash coil side here, R1 dash coil side here, dot mark, and here R2 again current is going towards upper one, so let me put with cross mark, and R2 dash is coming towards down, so dot mark, right? R2 dash. Now try to represent flux around these conductors, right? So if you see this R1 conductor or R1 coil side, it is having cross mark now, so try to apply a right hand thumb rule, right? So thumb represents direction of current. This current is going away from us, that is entering into the plane. So try to represent thumb in that direction and remaining forefinger curl gives flux direction. Therefore I can represent here flux direction is going to be in this way, right? Here flux is in clockwise direction, and here it is dot means anti-clockwise direction, and here cross is clockwise direction, and here dot anti-clockwise direction, right? See here, if you observe this flux direction, it will be, you can understand, right? See, these two conductors are producing flux in this way, like this flux lines are producing. If flux lines are produced in this direction, I can say this can this can be the north pole, right? And if you see here flux lines are produced in this way, so therefore I can say this is south pole, and here flux is producing in this way, right? In this direction, I can say this is north pole. And here flux lines are entering into the region, so that I can take south pole. And if you do the analysis of this previous one, what I said previously, in order to create p poles, we require p by 2 coils, right? That condition we need to satisfy. So how many poles we have created here? 4 poles we have created, north, south, 4 poles we have created. And how many coils we used here? 2 coils. Again, if I write this in generalized form, then it will be like this. Poles are P and coils are P by 2, right? Which is equals to 4 by 2, right? This is poles and this is coils, right? So this is the generalized expression, right? This is the generalized expression. If you want to design machine with P poles, we need to use P by 2 coils, right? We need to use P by 2 coils, right? And remember, here one more important point is, whenever we are placing 2 coil sets side by side, right? That is consecutive conductors, right? If you place winding or coil sides in slots, which is having opposite current direction. See, these 2 conductors we can call it as consecutive conductors, right? Consecutive conductors. If 2 consecutive conductors are having opposite current direction, then it creates poles, right? It can produce, this entire setup can produce a good magnetic field. I can say strong magnetic field, and therefore this can be satisfied, right? So why I am discussing this point is, instead of keeping R1 and R1 dash here, if I keep R1 here and R1 dash at lower side, right? What happens? Let us try to understand. Once again, I will redraw this diagram. See here, observe carefully. See, coil sides R1, R1 dash I have kept here side by side, right? Coming to the lower diagram, I did not keep side by side, right? I have kept opposite side, right? If you do this arrangement, what happens? I mean, the problem with this arrangement is, if you represent flux direction around the conductors, then how it will be? Here it is clockwise direction. Clockwise means in this direction it will flow. And here also it is clockwise direction. and here it is anti-clockwise direction, and here also it is anti-clockwise direction. So if you observe this flux lines carefully, see these two flux lines are there in opposite direction, right? These two flux lines are there in opposite direction. If these two flux lines are there in opposite direction, therefore what happens? This flux can exactly cancel this flux. Why? Because these two coils are connected in series. Now, if these two are connected in series, current flown through each coil side is same. If current flown through each coil side is same, what happens? Flux produced by each coil side also same. If this flux produced by each coil side is same, then what will happen? If those two flux lines are in opposite side, what will happen? These two flux lines will cancel. So therefore, there is no pole formation. There is no pole formation. There is no pole formation, right? And if you observe this side also, see this R2 dash conductor flux is flowing in this direction. R1 dash conductor is flowing in opposite direction to that. So therefore, here also there is no pole formation. There is no pole formation. Pole formation, right? And if you see other regions, see here flux lines are entering. I mean both the flux lines are entering. Leaving from the core. So therefore we can represent this with north. And here it is entering into the core stator, into the stator. These flux lines are entering. So we can represent with south. As it is forming only two poles, and I can say these two poles are not going to have sufficient strength, right? These poles not have sufficient strength, sufficient magnetic field strength, magnetic field strength, magnetic field strength. Therefore, such type of arrangement cannot be encouraged, right? So we need to keep in mind that always side by side conductors, that is consecutive conductors, should have opposite current. Then only pore formation is possible. That means strong magnetic field can be established by the stator, right? This is very, very important, right? While placing the conductors in stator slot, we should ensure that consecutive conductors, right? Two consecutive conductors should carry opposite current. If two consecutive conductors are carrying same current, what happens here is there is no chance to create pole, right? If poles are not created or weak poles are created, then that is not sufficient to run a machine, right? So this is the second important point. From this discussion, this is another important point we need to understand, right? So if I write that points here from this discussion, how it will be? See here, if two consecutive conductors, we can consider this as a two consecutive conductors. If two consecutive conductors, carry opposite direction of current, opposite direction. Why we are telling opposite direction? It is cross, it is dot. That's why we are considering it is opposite direction of current. Direction of current. Then only pole formation takes place. So pole formation takes place means strong magnetic field can be produced. Strong magnetic field can be produced. Magnetic field can be produced. Field can be produced. Right? This is the important we need to remember. Instead of having this consecutive or two consecutive conductors with opposite current direction, instead of having in this way, if two consecutive conductors are having same current direction, for example, if this is the case, second one is the case, if two consecutive conductors carry same current, carry same current, same current, same current. That is direction point of view. That is direction point of view. Same current direction. Then there is no formation of poles. There is no formation of poles. There is no formation of poles. Poles cannot be created. That means magnetic field cannot be established, right? That is magnetic field cannot be established strongly, right? See here in this diagram, see two consecutive conductors which are having same current direction. Here pole is not created. That is what we are writing here, right? And if you take consecutive conductors which are having opposite current direction, it can form poles, but orally if you see not sufficient number of poles are created, so that I can say not sufficient amount of magnetic field is produced. So that is what I have written. Magnetic field cannot be established strongly, right? So this is about AC winding in AC machines, that is in stator structure, and these are the important points we need to keep in mind, right? So thank you for listening.